Now that we've talked about what Java futures are and how they provide a key foundation for Java completable futures, let's briefly visualize the use of Java futures in action. And so this particular example is going to show you, literally show you what futures look like. And the way you should think about this is that an async call in Java immediately returns a future and then continues to run the computation in the background thread until it's finished. So you can see here you invoke a method like this, and right away you get a future back, the computation runs in the background, and the caller can go and perhaps do other things while it's waiting for the calls to finish in the background. We'll see that that's easier said than done with Java futures, and that's one of the things that motivates Java completable futures. The typical way to initiate an async call in classic Java is to use the submit method defined on the executor service. Executor service is an interface that can be implemented by a whole bunch of different kinds of threading mechanisms, such as different thread pools. And there's a submit method, and you can submit something called a task. And the way it works is as follows. You start by creating an implementation of the executor service interface. A classic example is the Java fixed size thread pool or fixed thread pool, which, as you might expect, has a fixed number of threads. You can designate that number of threads. A common number, by the way, is the number of cores on the underlying piece of computing equipment, like a virtual machine or some execution environment. So typically you have as many threads in the fixed thread pool as there are cores, although your mileage may vary depending on your needs. So you create a thread pool, then you go ahead and submit a task. Here's an example of a task. There's various ways to make a task, but here's a common one. This is what's called a callable. And a callable is a functional interface that has a method that takes no parameters, at least not through the parameter passing means, and returns a value that's parameterized to the callable generic interface. So this task is a callable that returns a big fraction, and you can see here that we're going to pass it, using the word loosely, some big fractions. We're going to then multiply those big fractions together, and that will get returned as a big fraction result. So we take that callable, we submit that callable to the executor service method. That goes ahead and sticks it into the executor service thread pool executor, which is the implementation of this thing. And when that happens, you get back a future. So the future comes right back from submit. So you can see here when we say submit, we get back a future to a big fraction. And then the computation goes off and runs in the background. And in the background, it'll call this callable lambda, which, again, will multiply the big fractions together. Now, the client code, the thing that's over here, the quote, main thread in this example, can go off and do whatever else it wants. It might decide to be responsive to user interface operations. It might invoke some more operations to run asynchronously. It's really up to the calling thread to decide what to do. And at some point, the computations hopefully are done, and then the client can get the results. Now, the tricky part with classic Java futures is how to know when the results are ready, and it's a little bit harder than you might expect. Hence, completable futures, which fix this particular quirk. But the typical way to do this is to have the client thread at some point, or it could actually be a different thread, call the get operation, get method on the future, which will return right away if the asynchronous computation is finished, or will block until the asynchronous computation is finished. And because you might not want to block indefinitely, you probably don't want to block indefinitely, they give you this way of being able to poll by providing n, which is the number of time units, which are seconds, milliseconds, microseconds, and so on. So that's how you can decide to wait for a certain amount of time. If you give a 0 here as the value of n, it will just check to see if it's finished, and if not, it returns null, saying it's not there yet. If you give something that's greater than 0, it'll wait for that amount of time in whatever time unit you provide. One of the things to keep in mind when you perform asynchronous operations is that the computations that you initiate asynchronously may complete in a different order than the order in which the async calls were made in the first place. So you may get an out-of-order response, which is perfectly okay. In fact, that's kind of the point. You want to get the results back as soon as they're done. You don't want to wait for them in the order you invoke them. If you wanted to do that, you'd use synchronous calls, which has the downside of potentially impeding or reducing the amount of parallelism that's available in your solution. So that's just kind of a quick walkthrough of futures in action. We'll break it down a little bit more. We'll take a look at some examples here shortly, but this hopefully will give you kind of a bird's eye view of what's going on before we start diving into the API level elements.